Okay, just to say one final thing about this question before we move on to the next one. Now, most people, I was really pleased, they noticed that it says here that it's at room temperature. Now, I've told you a million times that temperature is what tells you the kinetic energy. And so some of you assumed that if they're at the same temperature, then they must have the same kinetic energy. Now, that was really insightful and good. Now, the only point of the picture that you missed there is the fact that one of them is a gas and one of them is a solid. So at room temperature, steel is a solid, but the elements of air that make up air, or the molecules that make up air, are a gas. So actually, because we know the particles in gases move very much more quickly, and so it is slightly confusing when you're looking at things at the same temperature in different states, but in this case, the air particles will have more kinetic energy than the steel particles. And the reason for that is even though they're at the same temperature, the air is a gas and the steel is a solid. Okay, so mark number one is for particles vibrate around fixed positions in the steel. The air particles move about freely, and the final thing is to say that the kinetic energy of the air is greater than in steel. Those of you that missed those marks, it was mainly because you'd not quite read the question. Look what the question says. Compare the movement and energies. So here is the movement, here is the energy. You had to do both of those things to get those points. Okay, let's move on. Well, this was a good one. This was mainly answered really well. So we've talked a lot about evaporation. So you've got your particles on the surface of a liquid, and they're all moving past each other, and they are moving with a range of energies and a range of speeds. And only the most energetic are able to leave the surface. So there are 4 points to make. The most energetic particles leave the surface. And I'm just writing it quite short here. You might want to expand on this slightly, saying the most energetic particles, only the most energetic particles have enough energy to escape the surface. Then we have, therefore, the average, keyword, average kinetic energy of particles remaining goes down. And therefore, the temperature decreases. Okay, so for most of you, this was well answered, and you obviously got the right idea. It's just sometimes the language is just slightly woolly. In a question like this, we're not really talking about internal energy directly. So a few people were talking about it in terms of internal energy. Yeah, the internal energy is changing, but remember the most important thing. The most important thing is the average kinetic energy. Okay, the average kinetic energy is this thing here, all right? That's what determines the temperature. The average kinetic energy determines the temperature. So if the average kinetic energy goes down, the temperature goes down. That's the link that you're trying to make. This is the most important one. It's from here to here, okay? And why does that happen? Well, it's because only the most energetic particles leave the surface. Okay, so if we imagine remember we've got this distribution of speeds. So here's speed, here's number of particles. Most particles are like traveling, middling. Some particles are traveling slow, the ones down here. Some of them are traveling really, really fast. And it's only these ones here which are fast enough to leave. So if they go, then the average is going to go down. And remember the analogy, if the whole school goes on a running race and then I take the 10 fastest runners and I take them away, and we do the race again, then the average speed of everyone left is going to be lower because I've taken away those really fast runners. Okay, so this little sequence is a really important one. If you can get this nailed on, that would be really, really great. Okay, moving on. We've got one about moments. So the diagram shows a spanner being used to undo a tight nut. The nut was tightened using a moment of 120 Newton meters. Calculate the force needed to undo the nut. Show clearly how you work out your answer. Okay, so most of you remembered that to calculate a moment, it's equal to the force times the distance. Now, problem is, the thing that you forgot was the word that goes in front of distance, which is the perpendicular distance, right? Times the perpendicular distance. So here's the pivot, and look, here's the force. And remember, we call this line the line of action of the force, okay? It extends all the way back and all the way forwards. It's in the direction that the force is acting. And look, here's the force arrow here. So what's the perpendicular distance? Well, I have to find the line that goes from the pivot, and then it's the one that meets that line perpendicularly. So what distance do we need? It's this, it's 40 centimeters. So those of you that said the distance 50, that's the distance from where the force acts to the pivot, but it's not the perpendicular distance, which is the one that I've drawn here in red. So that's the first thing to spot. The second thing to spot is look at our units, meters, Newton meters. If I've got a Newton meter, then I must have done a force in newtons times by a distance in meters. And this is in centimeters, so I need to convert it. Okay, so what can we write down? We can say 120 Newton meters is equal to whatever the force is times by 0.4 meters. And so the force is 120 Newton meters divided by 0.4 meters. And if we do that, we get an answer of 300 newtons. Okay, all right, moving on. How much time have I got left? 3 minutes. I might pause there and pick this up in the next one.